All right, so last time we ended with bouncing. Remember the Pelton wheel? We're going to start with energy. Now this unit, don't try to say, okay, these are chapter 7 notes, chapter 8 notes. I kind of bounce around. These are just all chapter 7, 8 notes, so I bounce around a lot.
That's it somewhere else. This is too close for me.
You're all turn around. Bench.
Alright.
Energy is the ability to do work. Now there are lots of kinds of energies. Lots and lots of kinds of energy. In this unit, we are going to deal with mechanical energy. Next semester, we will be dealing with other kinds of energy. Things like heat and light and sound, electrical. But this unit particularly, we're dealing with mechanical energy, which is the energy of motion and position. Energy of motion and position. And if you know, we'll also be dealing a lot with machines in this unit. Anyone need more time? Now work. Work. The symbol for work is a capital W, which is why I don't like using W for weight, like they did in the last unit. We'll use F sub G, force of gravity. W is work. W for work. Our unit is the joule, capital J. We honor for James Joule, who basically had an experiment that showed that all energy was the same. Up until Joule's experiment, people thought, you have heat energy, you have this energy, you have that energy, and they're all separate. After Joule, we know that energy is energy. And it just transfers from one type to another on that. But there are lots of energy units. In fact, in this class next semester, we'll use another energy unit for heat called the calorie. Not the same calorie as you see on your food wrappers. That's actually kilocalorie. But we're going to see that one also. But there's lots of different types. In fact, on your electric bill, if you ever look at your electric bill, it will tell you how much electric energy you use. It's called a kilowatt hour. Kilowatt hour is a unit of energy on that. Now the SI dimensions of a joule, it's a kilogram meter squared per second squared. So when you say a joule, you're saying a kilogram meter squared per second squared. The SI dimensions, the metric dimensions. Just remember, their SI dimensions tell us why we have to be in kilograms, meters, and things like that, where it all comes out. This is the force applied over a distance. Force applied, so our work is equal to the force times distance. In other words, W equals FD, which is or Fx, and a number of other ways to say distance. So in other words, when I take this roll of tape and I lift it up here, did I do work on the tape? Yes, I did, because I had to apply a force. I had to apply a force greater than its weight. I had to apply that force, and I moved it a distance. But if I'm pushing on the table here, am I doing work on the table? Yeah. Table moving? No. No movement, no work. Am I expending energy? Yes. But I'm expending other types of energies. Okay, I am expending energy, but I'm not doing work. For work to occur, we actually have to move. Anyone need more time on this? This one? FD. The D. Sometimes when it records, because it's doing several things at once, it doesn't like to write evenly. Their processor, I guess. All right. Anyone need more time? So we have a video about work.
Eureka! refers to how much stuff. In other words, weight is just another way of saying force of gravity. An object's mass never varies, but its weight can go up or down depending on the force of gravity acting on it in various parts of the universe. And now, work. These barbells have a mass of 120 kilograms. Since they are resting on the surface of the planet Earth, we know that the force of gravity acting on them is about 10 times that number of newtons. It takes a very strong man to lift something that weighs so much. Because if the barbell is being pulled down by a force of 1,200 newtons, it must take 1,200 newtons of force to hold it up. Of course, if we were on the moon, where the force of gravity is only 1/6 that of the Earth, anybody could do it. But we're not on the moon. That looks like hard work. But how much work? 1,200 newtons worth? To lift the barbell? How far? Exactly 2 meters. But what if you only lifted the barbell half that distance, say 1 meter? Surely that doesn't take as much work as lifting the barbell 2 meters. When you lift the barbell all the way up, you're doing 1,200 newtons times 2 meters worth of work. When you lift it only halfway up, you're doing half that amount of work. 1,200 newtons times 1 meter. In fact, this is how you measure work in physics. Work equals force times distance. Here you're doing 1,200 newton meters of work. And here you're doing 2,400 newton meters of work. That's simple enough. But suppose that after the show, the strong man discovers that his car is stuck in the mud. He pushes it and pushes it, but it won't budge a millimeter. And suppose that at the very same time, the clown, who hasn't got a car, is in the act of picking up the telephone to call a cab. Which of them would you say is doing work at this particular moment? The strong man or the clown? The clown. Because work equals force times distance. And although the telephone receiver only weighs about 2 newtons, while the strong man's car weighs perhaps 15,000 newtons, when he lifts the telephone receiver, the clown is applying a force of 2 newtons through a distance of 50 centimeters, let's say, or half a meter. And therefore, he's doing 2 newtons times half a meter of work, which is 1 newton meter of work. The strong man, on the other hand, may be exerting thousands of newtons of force. But since the car's not moving, there's no distance involved, and the poor man isn't doing any work at all. A force of even thousands of newtons times 0 distance equals 0 work, whereas a force of only 2 newtons through a distance of only half a meter does equal some work, even if it's only 1 newton meter worth. But it's a bit awkward to keep on talking about newton meters of work. So physicists have borrowed the name of a famous British scientist, James Prescott Joule, as the measure of work. 1 joule is the amount of work done when 1 newton of force is applied through a distance of 1 meter. That's to say that 1 newton meter equals 1 joule, which can also be written like this. So the clown did 1 joule of work when he lifted the telephone receiver. And the strong man did 2,400 joules of work when he lifted the barbell. But of course, when he tries to move his car, it's a different story. He does 0 joules of work.
Okay. So once you realize they talk about the Newton meter, they're trying to emphasize that it's newtons times meters there. We never use Newton meter as a description of energy. That is never a energy unit. In fact, we use the Newton meter is actually the unit for torque, which has to do with circular motion. So we never use it for energy in any way, shape, or form. So machines. And we saw our video about machines. Machines. Now machines are devices that change input and output force. And did you catch the thing about that? A human being can produce half the horsepower for 6 to 8 hours. It's not very much. They said even just if you had a 2 horsepower water wheel, 20 times, they could generate 20 times the energy that a human being can. One of the reasons we have these little machines help us a lot. However, energy is always conserved. Keep that in mind. When we deal with machines, the energy in the machine is always conserved. What does that word mean? Anytime you see the word conserved, conserved is a word that means whatever was in the beginning is the same as it is at the end. Whatever was in the beginning at the end. I mean, I've mentioned a number of times, rule number 1 of the universe is conservation of energy. The energy in the beginning, energy at the end. Thing is, with all machines, whatever work you put in, the most you can get out is the same amount. That's the best you can do. Work in equals work out. The secret here is that as force goes up, distance is going to go down. Anyone need more time? If we are looking at this, now this is a lever and some terms. Now we have an input side. Which we also call effort. Makes sense. You have to do effort. You have to expend some effort to get it to do something. It's what you do. We have output. We also call that the load. What you're trying to lift or trying to move or whatever you're trying to do. And the thing is, if I want to lift this large force, the machine allows me to use a small force. But notice, I have to go a much greater distance, and it's only going to go up a small distance. The idea being here's our inside, outside. The work in is going to equal the work out. Best you can do on that. So the work in equals the work out. All simple machines work this way, even though a couple of demonstrations can be levered. But all simple machines work on the same principle. Work in equals work out. How we find those distances and force. But like this, if you think of, if you're jacking up your car, you have to change the tire. You set the little jack up, you put the little thing on, you have a handle. And you push down. And when you push down about this far, about a foot. I mean, it's usually about, then you go push down, it goes click. And the car goes up a little bit. How far does that car go up? Not that much, maybe about that far, so maybe half an inch. So you moved a foot, the car goes up half an inch. But remember, you used a small force for a foot. The car, which weighs a lot, you put a very large force up that small distance. All right, this is the whole point of a machine. Anyone, one more time? So if we're going to put some numbers to this, over here we have our effort side. Then we have our load side. So we want to say, does our out actually equal our in? Well, let's see. So the little girl, she uses a force of 10 newtons. 10 newtons. For a distance of 1 meter, which means her work in is going to be 10 joules. 10 times 1. Over here, our load, you're getting out 80 newtons, but it only moved 1/8 of a meter, so my work out here is, again, 10 joules. So when I look at this, 10 joules equals 10 joules. They are equal. They're going to go in. This is how all simple machines work. She used a small force for a large distance, and got out a large force for a small distance, but the energy is always the same. Energy is always conserved. Anyone need more time for our diagram? We should be putting our diagram. So, simple machines. And I gotta say, if I gave you 8 different lists from people's simple machines, they probably have 8 different things on there. One additional one I think I'll add to this. Wedge. The thing is, levers, pulleys, wheel and axle. There they said in the videos. These are all types of levers. Wheel is a continuous lever. A pulley is a type of lever. It works like a lever. The inclined plane, the screw, the wedge. These are all an inclined plane, i.e. a ramp. A ramp on that. And if I put 2 or more of these together, I get what's called a complex machine. 2 or more simple machines together. 2 or more simple machines together. And I can show you one. This is a complex machine. The knife. You know, what you use to cut up boxes and stuff like that. But it is a complex machine. Why? Because this is made up of 2 simple machines. One, it's a lever. The knife itself is a lever. The edge of the knife is an inclined plane. It is a wedge, which is a type of inclined plane. Remember they talked about the pizza cutter. Remember the pizza cutter. 3 simple machines. You have a lever, you have a wedge, and you have a wheel and axle. Handle's the lever, wheel and axle on the wheel, and you have the edge is a lever. In fact, even a pair of scissors. Complex machine. There are actually 4 simple machines here. I have a lever, actually 5. A lever, a wedge on this side, wedge on that side, wheel and axle. So a pair of scissors is actually 5 simple machines put together. Okay, so these things put together on that. Questions? Alright, so I have a little short video about inclined planes.
Unbeliever. Next comes mechanical way. You haven't really got enough force to lift that barrel, have you? How much force do you need to lift it? Well, how much does it weigh? So you'll need at least 800 newtons of force to lift it into the back of the truck. How far is that? About 1 meter? How many joules of energy will it take? Well, figure it out. Energy is the ability to do work. Work equals force times distance. 800 newton meters of work, or 800 joules of work, which is the same as 800 joules of energy. But you still can't lift the barrel. There's something wrong somewhere. Perhaps it's because you have to exert your energy all at once. If only you could load the barrel onto the truck a little bit at a time. If you could slice it into 4. Then you'd have 4 200 newton slices of barrel. And you'd only need 200 newtons of force to lift each one. That's easy, isn't it? You're using your energy more effectively now. You're spacing it out over a longer time. But you don't get anything for nothing. Although your force is cut down to a quarter of what you need to lift the complete barrel, each time you lift a quarter of the barrel, you exert that force through 1 meter. Which means that you lift the 4 quarter barrels through a total distance of 4 meters. What what you're winning on the force, you're losing on the distance. It's a sort of trade-off. The greater the distance, the less force you need to exert. Very neat. But you can't go around breaking things into pieces just because they're too heavy to lift. If only you had a machine that would allow you to trade increased distance for decreased effort or force. Here's your machine. Yes, I know it's just a plank, but it's also a machine. Try and get the barrel into the back of the truck now, and you'll see why. Magic, isn't it? No, it isn't. It's exactly the same trade-off you got when you split the barrel into 4. The plank is 4 meters long. Instead of moving the barrel 1 meter by lifting it straight up, you're moving it 4 meters by pushing it along the plank. You only need to push it with about 1/4 as much force, with only about 200 newtons instead of 800 newtons. But since moving 200 newtons through 4 meters is the same as moving 800 newtons through 1 meter, it will still take roughly the same amount of energy to move the barrel by either method. That's why we can call the plank a machine. It doesn't reduce the energy you need to do something, but it does help you to use your energy more effectively. You think you've just made a new discovery? Think again. How do you suppose they built the pyramids 5,000 years ago? They didn't actually use a plank, of course, but a ramp of earth, which is exactly the same principle. And you use the same principle yourself every time you stand on an escalator. Because the plank, the ramp of earth, and the escalator are all 3 examples of the same type of simple machine. They are all sloping, and they are all flat. So physicists call this variety of machine the sloping flat thing. Well, those aren't the exact words they use. They take the Latin-derived word for sloping, which is inclined, and the Latin-derived word for flat, which is plane, to come up with this phrase. So if you're allergic to elevators, why don't you take the inclined plane?
Okay, so inclined plane, one type of machine, but the principles there work all the same, and that increase is something we call mechanical advantage. Now there are 2 types of mechanical advantage, because there's the mechanical advantage we should get out, and there's the mechanical advantage that we actually get out. A lot of times when we work with machines, we work with energy. Now, energy is always conserved. Does that mean that all the energy that comes out is going to be useful? No. Some of the energy, because you know as you ride along in a bicycle, what happens to, say, you touch the hub of the bicycle as you've been riding for a while? What does it feel like? It's hot. So some of the energy in the bicycle you're using pulleys and levers and all kinds of things. Some of that energy that you're putting into your bicycle is being used up in the fact that it gets hot. Okay? So, on that. So the actual mechanical advantage, and we call that AMA, is the ratio of the load force, load, that's what we're trying to lift, to the effort force. Load to effort. So AMA is going to be our load force over the effort force. Well, wait. AMA equals FL over FE, like that. Now, how would that work? Well, let's say we take the example in our ramp there. In our ramp, you know, they used, it's the AMA in the movie, the load was 800 newtons. But by going up the ramp, how much force did he have to use to go up the ramp in the video? 200. 200 newtons. In which case, 800 divided by 200, our AMA is 4. And we would write that this way. It's written as a ratio, 4:1. Remember that from mathematics? You know, you have these ratios. And we would say that it's a 4-to-1 mechanical advantage. And when we're talking AMA, it means for every 1 Newton I put in, I'm going to get 4 Newtons out. So if we're talking actual mechanical advantage, I mean, we're talking about the force. For every 4, or other one way to look at it, for every 4 I get out, I'm going to have to put 1 in. Anybody need a little more time? Okay. All right. Well, this is what I actually get out. What should I get out? And that's what we call the theoretical mechanical advantage, or TMA. And this is the ratio of the effort distance to the load distance. So it's effort distance. Okay? So our TMA. Effort distance over the load distance. And notice we base TMA on distances. Actual is the force. Theoretical is the distance. Because the distance has to do with geometry of the situation. Geometry doesn't change. It has a fixed geometry. But how much force you get out, you know, there's things like friction and stuff like that. So if we took the example in the video, the ramp was 4 meters long, but they were lifting it vertically. So if we look at that inclined plane, they were using that. We had a 4-meter ramp. They were lifting vertically 1 meter. Again, it came out to be 4. Still a 4-to-1 mechanical advantage. But when you're taking theoretical, it says for every 4 meters I move, I'm going to lift 1, or I'm going to change 1. So you kind of, it's what you do. So when you're talking theoretical, remember the distances. Same mechanical advantage. Maybe. Maybe not. But this one, we just read it a different way. Remember, these are distances. So the bigger number is what you do. A lot smaller number is what you get out. Anyone need more time? I have a little video that kind of reinforces these ideas here. All right. Anyone? We good back there?
Eureka! The story so far. Machines don't reduce the energy you need to move things, but they can reduce the force you need. They do this by increasing the distance through which you exert your force. The two simplest machines are the inclined plane and the lever. The principle of the lever states that the longer the arm of the lever to which force is applied, the less that force need be. And now, mechanical advantage and friction. Here are two scientists, Professor A and Professor B. They are both equally strong. And here is a very heavy book about science. We are now going to perform a scientific experiment. We are going to find out which of the two professors can lift the book with the lesser amount of force. First, Professor A. 24 newtons of force. Now, Professor B. Only, what? 6 newtons? Well, there's no doubt about it. Professor B is the winner. You're quite right. It's not fair. Professor B had an unfair advantage. He used a machine, a lever, to give himself a mechanical advantage, in fact. But just how much mechanical advantage did the lever give Professor B? It's easy to work out. Both professors lifted the book to a height of about 10 centimeters. Professor A lifted it straight up, so he had to pull against the full force of gravity, which was pulling the book down. But since Professor B's lever arm was 4 times as long as the arm the book was resting on, he only had to pull with 1/4 the amount of force, 6 newtons instead of 24. In other words, his input force was 6, and his output force was 24. And all you do to calculate the mechanical advantage of a machine is divide the output force by the input force. So Professor B's lever had a mechanical advantage of 4. You'd like us to repeat the experiment, Professor A? You think you can equal Professor B's feat of lifting the book with a force of only 6 newtons? Very well. Professor A is now setting an inclined plane against a block of wood 10 centimeters high, and the inclined plane is 40 centimeters long. Fine. That's 4 times the distance, so it should divide the force he needs by 4, which means that his Newton's spring scale should read 6. What's this? 8 newtons? Well, there it is. Professor B is still the winner with a force of only 6 newtons, thanks to the mechanical advantage of 4 given him by his lever. Whereas with Professor A's inclined plane, we see that he has a mechanical advantage of only 3. Why is this? Why did the inclined plane have less mechanical advantage than the lever? Because of something we've forgotten about till now, the force of friction. Every time something rubs against something else, there's friction. In theory, Professor A should have been able to pull the book up the inclined plane with a force of only 6 newtons. But since friction was pulling in the opposite direction with a force of 2 newtons, the professor's pull had to total 8 newtons. Professor B, on the other hand, was lucky because the amount of friction between the point of the fulcrum and the lever arm is almost 0. So the lever is a more efficient machine than the inclined plane, because the inclined plane is plagued by the demon friction. But friction can be an angel as well, of course. Without friction between the tires of your car and the road, you wouldn't be able to drive. Or stop driving. Just as if there was no friction between the soles of your shoes and the floor.
Okay, so what would be that difference? Well, we call that difference efficiency. Efficiency, and it's the ratio of the useful output work to the input work. Now, this is true for all energy. No matter what energy you're talking about, it's what you get out versus what you put in. So the best you can get is 100%. Best you can get if they're equal. So our efficiency is equal to the work out. Divide by the work in, and we divide by 100%. Best you can ever do is 100, because work out divided by work in, if they were equal, it would be 1. 100%. Usually, because of friction, are you ever going to get out as much as you put in? No. I mean, the whole idea between why do people try to make more efficient machines is to make this work out get better, closer to work in. Things like that. It also equals the actual mechanical advantage divided by the theoretical mechanical advantage times 100%. So it's also the ratio of the actual to the theoretical. So why would they be the same? Why would that be the same? Okay, we need more time. And the next slide will be our last slide for today. So, there. Also the ratio of actual theoretical. But why is that the same? Well, first, if we looked at this ratio, AMA to TMA. Well, remember, AMA is the ratio of the effort force to the load force, and that's going to be, TMA is the ratio of the effort distance over the load distance. I mean, that's what they equal. But if I switch this around, look. Actually, I did that one backwards, sorry. Load over effort. So when I get the load over the effort here, divide by over L. But in mathematics, when I divide by a fraction, I'm going to multiply in by the reciprocal. Well, so I end up with the load force times the load distance, effort force divided by the effort distance. Well, load, force, and distance, that equals work out. Effort is work in. So you can see AMA and TMA is the same thing as work out over work in. All right. Don't forget your things. Chapter 8 is your homework. Work on your projects. Remember, don't forget your haikus. See you all on Friday.